Okay, thanks. And is this is on okay? Right? Yeah. And thanks to the organizers for the invitation. It's been a great meeting so far. So I kind of struggled with what to talk about. So my theme is kind of here. So what I'm trying to show here, not very well, is a comparison of an X-ray pulse at the advanced photon source, or over here at any storage ring, and at the LCLS. So it's hard to show, but so this is representing a 100 picosecond wide pulse with 10 to the 10 photons. And then trying to compare it with an LCLS pulse, which is 1,000 times more narrow in the femtosecond regime and has 100 times more photons. So this is 10 to the fourth, while this is 1. So this thing is way shooting through the roof. So consequently, the physics you see is very different. And so what's interesting to me, as I'm an old-time synchrotron user over my career, so I'm familiar with using X-rays in the one photon, single photon interaction regime, and doing a lot of very nice things, and all that work is continuing. And sort of for storage rings, so there's some new developments that are happening now and also in the future, which include now using high repetition rate lasers for pump probes, so you can use all your X-rays really efficiently. I'm not going to show those results. Also improved femtoslicing beamline, so that's taking synchrotron pulses and picking out a femtosecond slice. So of course they're weak in terms of flux, but they're ultra fast. And then in the future at the advanced photon source, we have a scheme. We're trying to use cryogenic RF cavities to pick out about a 2 picosecond slice. So there is a future here, but then what I really want to focus on is this sort of new regime that Joachim Ulrich introduced yesterday, where you have these super intense and very fast X-rays, and sort of two sort of themes here. So we've done experiments, several people have done experiments, Joachim's done experiments, and you struggle because they're chaotic. Pulses build up by this Saucy process. But nevertheless, you can see sequential multiple photon processes. We have an experiment where we've seen the onset of Rabi oscillations. The rep rates are low, but it's femtosecond. So in the future, what people are excited about is, okay, if you could seed the FELs, make the pulses more Gaussian-like, much more coherent, but also narrow band as well, but still very intense, and then have other tools like polarization control. You could make circularly polarized X-rays, for example, efficiently with a helical undulator, and get into the regime of sort of quantum control. So this is closer to what I think the theme of the workshop is, so I'm going to try to focus on that. So I guess I can just sit here. Yeah. So this is sort of a blast from the past. I mean, the reason I'm showing this, so this is now synchrotron work. People are very interested in double ionization. 15 years ago, let's say, this was a hot topic. And so the idea is that you can knock out 2 electrons from an atom due to electron correlation. So a lot of theoretical work was done to explain that in terms of these different mechanisms, if you will. The shake-off, which is just the relaxation of the atom when you remove one electron. There's this process where this initially excited electron knocks out another one, sort of like a billiard ball effect. And then the ground state correlation. So there was a lot of theoretical work done to calculate these things. There was a simpler model which came out about 10 years ago, which said, look, we can kind of simplify this, at least in the case of double ionization of helium. We can calculate this ratio of double to single ionization if we include just sort of 2 terms independently. The shake-off, the relaxation of the atom, and then this knockout effect. So there was so experimentalists sort of pick up on these sort of simple pictures of what happens in double ionization and applied it to higher Z atoms. And so one thing we did at the APS was to set up an electron spectrometer and look at this double K-shell ionization in atomic neon. So we use 5 kilovolt X-rays. And the idea there is, so you make this hollow neon atom, so both electrons are gone, And so what you can look for is what's called the Auger hypersatellite. So the Auger process, those of you who don't know, is you have a hole here and an outer electron fills it. Another one comes off. That's an Auger electron. If there's two vacancies, then there's a shift in energy due to the change in the screening. And so you see a shifted Auger electron, so it's called a hypersatellite. So here it is. Here's the regular Auger electron spectrum that's been measured numerous times. And then if you blow up this region, sure enough, you can convince yourself you see one of these Auger hypersatellites. And you can notice this is blown up by 350 times, so that gives you an idea of how weak it is. It's about 0.3%. So if you hit a neon atom with a 5 kilovolt X-ray and it absorbs one photon in the K-shell, then you'll see double ionization at this sort of level. And there's a reason I'm showing this, because I'm going to contrast it with what one can see with an X-ray FEL. And so this is already long before the LCLS turned on, so people were asked, well, sort of a workshop like this, what can you do? What's going to happen? So you can do these sort of really simple estimates. Even experimentalists can do this. If you have some idea of what the number of photons will be, the pulse duration, and so forth, and then you plug in numbers for the neon cross-section and the Auger rate, it turns out those are sort of comparable. So what this suggests is that you can actually absorb 2 photons in the K-shell before the first vacancy decays. So now it's, instead of electron correlation, it's just 2 photon absorption. So this was the motivation for one of the first experiments that was done. And I promised Robin I wouldn't get bogged down in technical stuff, but just to give you an idea, this is one of the apparatus. So yesterday, Joachim showed the CAMP apparatus, which was very complex and very versatile. There was another apparatus that we used, which featured these 5 electron time of flight spectrometers, also had an ion time of flight. So a relatively simple atomic physics apparatus. So a beam went through, there's a gas jet, and you look at electrons and ions. And it's angle resolved that has some nice features, such as photoelectrons tend to come out along the polarization, whereas Auger electrons are kind of spherically symmetric in their angular distribution. So you can look here for your Augers, and you can look here for your photoelectrons preferentially. So here's some early data. And so I'll be looking up here, this electron spectra. This is in time of flight units. And so here's looking at these 1s photoelectrons from neon. And so you see these sequential peaks and the increase in binding energy as you get more and more charge. So you see that. And then if you look with a little bit higher resolution, then you can start to see the Auger electrons and also these valence photoelectrons. This is at 0 degrees, so this is along the polarization. If you go to 90 degrees, you tend to suppress the photoelectrons, especially the S photoelectrons. So you can see more clearly these Auger lines. So here's our Auger hypersatellite that with the synchrotron we saw with 0.3%. Now we see it with 10%. So that's kind of nice. And with that, then you can work out the double to single K vacancy rate. And what I'm showing you here now is another opportunity. So this is sort of, you have to be an electron spectroscopist like myself or maybe Michael from the old days to get sort of interested in this kind of a thing. But now, instead of seeing this sort of single peak, this is some other stuff due to other electron correlation effects, shake up and that kind of thing. But now we can see, sort of start to see the entire spectrum and then compare with calculations for this Auger hypersatellite and see these finer features. And if we have a little bit more time, we'll analyze this data and get some comparisons for these rates and these positions, as we have a detailed comparison with theory. One also starts to see these sort of weaker effects, which is now where you absorb three photons. So you've ionized another valence electron. So you can start to see those transitions as well. Okay, so the other thing one can do, so if you can see these double K vacancies pretty well in an atom, well then maybe you can also see them in a molecule. And long ago, Professor Sederbaum pointed out that if you do that, look, you're going to get better resolution of chemically interesting binding energies. And so this would be for the single core hole where you don't get much resolution. Now people have actually done heroic experiments where they do look at these splittings, but now this is suggesting if you can make 2 core holes on really sort of similar, chemically similar, or actually chemically distinct, but structurally similar molecules, then you can start to distinguish them and learn something about molecular structure and electron-electron interactions that you couldn't previously. So here's an example. This is one we actually did. Other people have done nitrogen also, but I'm just showing this because we actually did it and it's actually worked. And so now this is showing nitrogen binding energy spectrum. So it's around 400 electron volts. This is the main 1s photoelectron peak here, and then there's some other stuff up here, including the features due to ionizing the second K-shell electron prior to Auger decay. So this is the case where you have them on different sites, and this is where you have it on the same site, so you're just shifting up. And so one can compare these positions with calculations and get this sort of chemically interesting information. And that's what people have done, and so I wasn't going to go through this in any great detail, primarily because we haven't done much of it ourselves. I don't like to talk too much about other people's work, but there's a lot of work that's been done on theory and also now experiments, including using synchrotron radiation and doing like coincidence measurements. So the game, that for this particular science, you don't necessarily need a free electron laser if you're clever with how you do experiments at synchrotrons, which are now very sophisticated. Coincidence and such techniques are very commonly used. And okay, so we were motivated to do an experiment by one of Robin's projects. And the reason I'm showing this in part is because there are actually 3 atoms in this particular molecule. So if I go back here, and these are all sort of the small molecules, and you really need to look at these. That's important to do this research. But if you want to use this technique to learn more about chemically interesting molecules, then you want something a little bit more complex. So that's what Robin looked at here, this aminophenol system, which has a carbon, nitrogen, and oxygen. Here's the calculated double core hole spectra. So we were motivated. We wrote a proposal to do this experiment at the LCLS. Jochen helped us. But it turns out we didn't actually do this particular molecule. We did one a little bit simpler, which is called formamide. It also has nitrogen, carbon, and oxygen. And Steve Pratt, I think, pointed out to us that, well, it's a little bit simpler. Maybe it's a better way to start. So we did this one, and just want to point out why this is kind of an interesting molecule, is that it's sort of a prototype for a peptide bond, okay? So there's this very, if you're a biophysicist or chemist, you would know this kind of thing. With water elimination, then you get this peptide bond. So that's, formamide is sort of interesting for that. So we're working on that, and because our theoretical colleagues are so cooperative and helpful, they can then turn their codes to calculating for this molecule. So we have very nice calculations on where these positions should be. We have some data that we measured at the LCLS with, again, Jochen played a huge role in this. You had to have a heated valve, and that's all technical stuff. But we have the data, but we're still working on it. And so our hope is that we can observe these positions and then make some comparison with the theory. Okay, so I'm going to sort of shift emphasis here and talk about things which are a little more close to like quantum optics kind of issues. And so I'm going to talk about some progress toward using these intense X-rays to control populations of quantum states. And someone can look at these basic processes, resonance, fluorescence, resonant Auger decay. And then I'm going to finish with something which is an extension of work we did actually with the femtoslicing beamline at Berkeley. But we'd like to do some more work with that with ultrafast X-rays. And here I'm pointing out that with regard to these sort of quantum optics experiments, what's really hurting us at the moment is the fact that we have this very chaotic pulse structure. So this saucy type FEL process that gives you these nice pulses. They're very, very intense, but they're not temporally coherent. You have these spikes, so within each spike you have a nice coherence, but there's no definite phase relation between the different spikes. And so that's very hard to use such a pulse for this sort of, quantum optics kind of experiment. So what people are looking forward to, and there's already been an experiment at LCLS, is to use seeding techniques to clean up these pulses and make something much closer to a Gaussian-like pulse, much more coherent, also much more intense, and also narrow band. That'll help with things like photoelectron spectroscopy. So when we were trying to do those double core hole experiments, one thing that also hurt us was the energy bandwidth. Okay, so now if you'll bear with me. So I got interested in kind of resonance fluorescence. So this is a little historical stuff. So, if you've seen street lamps with these yellow lights, it's the sodium vapor, and it's, just this 3s, 3p resonance line. So I just want to point out that long before, I think, quantum mechanics, people were doing observations. So they had like a lamp, a sodium lamp here, let's say. Then they had a cell with the vapor in it, and they saw that if they shined this through there, this vapor would glow with the same wavelength that came in. So that's resonance fluorescence. So this goes back to at least 1908, and you can see papers by Lord Rayleigh and such. So I got kind of interested in that. But then let's get closer to the quantum world. So Heitler has a nice little discussion on resonance fluorescence. I just want to point out a couple of things. If you have a spectrally narrow line relative to the natural line width of a resonant line, then what comes out is also a sharp line. So remember, the idea of fluorescence is that sort of a two-step process. You absorb energy, you have a state with a given lifetime, and it fluoresces with a line which has that same natural line width. But if you use this resonance fluorescence effect with a narrow line, then what comes out is also narrow. Well, that's just energy conservation, if you think about it. The other thing which is in here, so there's 2 points. One is that Heitler points out that because of that, you cannot think of resonance fluorescence as a two-step process, up and down, but it's really a single quantum process. And in addition, he pointed out, well, the re-emitted radiation is coherent. Well, I thought that's kind of interesting. I assume this was in the 1936. I have the 1954 version, I think, but I assume they were already thinking about coherence at that time. Maybe not. You can correct me on that. Okay, so one more aspect of this, and again, Michael and a few others would appreciate this, I guess. 1980, I'm sorry, but this is when I grew up. And so Bernd Kreisman pointed out that, look, for X-rays and intershell electrons of atoms, you can have an analogy in the Auger decay to the resonance fluorescence. So this is kind of a busy figure, but just bear with me. So this is the xenon L3 edge. It's featureless, but we know there's some Rydberg states hidden in here. And so you can scan the energy through here and look at the Auger spectrum. And sure enough, they see this population of these satellite lines, which disperse linearly. That's resonance fluorescence-like phenomena. And you see line shape narrowing effects. And so this was sort of the analog to the resonance fluorescence, but now for the radiationless decay of an atom. So with a medium-sized atom, will have both radiative and non-radiative, so you can look at either one. What was I going to say? Okay, there's other phenomena here. There's so-called post-collision interaction, so the electron comes out, photoelectron, but Auger decay is rapid, so the core charge changes very suddenly. So you can have some interesting things such as recapture of these low-energy electrons back into the core. So you see this population of high Rydberg states in a sort of delayed onset of the diagram cross-section. This is really old physics, but there's a reason I'm showing it, because what I'd like to do is then look at some of these phenomena either with intense ultra-fast X-rays at LCLS, let's say, or at flash, but also in combination with external optical lasers. Okay, so now we're continuing with our sort of tutorial on resonance fluorescence. So if you have an intense coherent laser, but it's continuous, then you get this sort of state split. It's a two-level system. We're going to talk about two-level systems. And you get this state splitting, so you see this triplet in your resonance fluorescence spectrum, the so-called Malo triplet. So that's very well known. Now, if you no longer have a continuous wave excitation, but you have a pulse, then people began looking at that, and so now you start seeing little sidebands, if you will, on your spectrum, which are related to what became known as the pulse area. So you can calculate the pulse area from the Rabi frequency and your pulse shape. And the nice thing about this sort of concept is that if your pulse area is some integer multiple of pi, then you can think about the populations, where the populations is in your upper and lower state. So if it's an odd n, then you've transferred your population to the upper state. If it's even, then you've brought it back down to the lower state. So I'm going to use that here to just present a couple of results. This is really not my work. I'm on the paper, but I really just contributed some experimental aspects to it. There's really work by Stefano Cavoletto, Christian Booth, Harmon, and Keitel. So there's a new paper coming out. So this is now a calculation of resonance fluorescence for the case of pulses which one could find at LCLS. So they're ultra intense and they're ultra short. And so the idea is that what you'd first do is you would somehow make a neon cation. You'd have a missing 2p electron. And I'll show you that you can actually do that, either with a laser or with the FEL. And then you consider Rabi cycling to the excited state. So this is the two-level system here, and you have to have the right, there's selection rules on the quantum numbers if you have linearly polarized light. But you also have these loss modes, the photoionization from both the ground state and the upper state, but also Auger decay. So Stefano's done a calculation of all this, and I refer you to the paper which is in the archive. I'll just show you a couple of results. So these are sort of motivating some future experiments we'd be interested in, and I think other people as well. So just bear with me. So what I'm showing you up here is a plot of the population of the upper and lower states. I'm showing you two cases, with and without, including Auger decay. So the red one is really realistic, and the dashed line is the total population of the upper and lower. So this is for the particular case of this kind of intensity, this pulse duration, and for a pulse area of 14 pi. So that's going to leave you in the lower level. But it's going to give you 7 oscillations, if you will. And so the 7 oscillations show up in the resonance fluorescence spectrum if you can record it with high enough resolution. So this corresponds to up here. So the red would be the realistic case where you're down to units of 1.25 in intensity. If you could turn off Auger decay, which is an interesting idea, could you turn it off? And then so you're down by like a factor of 4, I guess, in intensity. But nevertheless, this is, and you've a little bit washed out your contrast here. Now the other thing to point out is that this calculation assumes a transform limited pulse, fully coherent. If you then do the calculation for a Saucy pulse, which is also in that paper, then you start to wash out some of the structure. But it doesn't go away, so maybe you want to try a first experiment. But really what you want is we want to tell our accelerator physicist friends we really need, better pulse control. We want seeding. So here's a sort of, I think this is just a calculation from one of John Arthur's talks comparing this chaotic Saucy pulse with what one would get with a seeded pulse. So that's really what we'd like for the future. And I believe they're doing that at Flash too. I'd like to hear about that. Okay, now, this is actually work done earlier by Robin and Nina. And this is very, very nice work. Pointing out now for, instead of the resonance fluorescence, this is the resonant Auger decay. So they did this a few years ago and motivated an experiment which I'm going to show you the results of. But now if you have control over the coherence properties of the pulses, then if you look at these Auger lines, you get these nice multi-peak structures here because you have control of the Rabi oscillations and the population of the upper and lower state. But they also did the case, which is realistic for what we can do now with the Saucy pulse. And so you get this really, this is just an example, it's one shot, you get this sort of chaotic pulse. And if you look at many shots, which is the experiment we did, then you get something which should broaden the normal Auger line a little bit due to the Rabi oscillations. Here you just have no control of the pulse area. But you can still see some line broadening depending on what intensity you're able to achieve. So where am I doing time-wise? 5 minutes. Oh, 5, okay. Okay, so we'd actually tried this experiment. Here's a paper if you're interested. And so 2 things. The experiment we did was we had neon, neutral neon, but as I pointed out earlier, you can absorb more than 1 photon from these FEL pulses. So the first photon would make a 2p vacancy. And then we tuned the energy to be resonant for this second process, this 2p to 1s excitation. And so when you make that 1s hole, then it's going to Auger decay. So we could look at the Auger electron. This is just pointing out how that resonance in neon cation is nicely separated from other states. So you can do kind of a clean experiment. So here's some of the data. So this is like a 2D plot of the electron kinetic energy versus the X-ray energy. And here's the 2p photoelectrons dispersing linearly. And right at this energy where corresponding to this resonant excitation of the cation, 848 eV, then you see the Auger lines coming out. So that's showing that we're seeing the Auger decay of this resonant process. And so what I want to show is a couple of things. If you project onto this axis, then this is what you get. So this is the Auger. It's basically our resonance, if you will. And it's broadened by the incident bandwidth. It makes it a little bit broad. And also one can see here a signature, a weak signature of a process where you've first started with 2 vacancies in the valence. So interesting stuff there. And then the question is, well, can we see these Rabi oscillations in this process before it Auger decays? So that's what we kind of looked for experimentally. And well, you can convince yourself that it's there. It's relatively weak. So this is comparing a low field theory with inclusion of the Rabi cycling. Nina and Robin worked this out for our particular experiment. We had to do volume averaging. That's just an experimental necessity. But also because of the chaotic nature of the SOSI, we just didn't have a very pronounced effect. But good enough to get excited about this for sort of a proof of principle, something one can do in the future. So I'm going to finish up here with another blast from the past. It's not so long ago, but at the ALS femtoslicing beamline, we were able to look at this X-ray, so-called X-ray transparency effect. This is again theory from, I'll get to the theory slide in a second, by Robin and Christian Booth and Linda Young. But the idea is what you have now, this same sort of neon. This is now for the neutral neon. Here's a Rydberg series in absorption. You don't see S states, right, because those are dipole forbidden. You can see them in an electron loss measurement. But if you now impose so these are the core excited states of the neon at about 870 eV or so. If you impose an external infrared laser field, you can now couple to this sort of hidden 3S core excited state. And that has consequences for the absorption spectrum, which is what Robin and Christian and Linda worked out, showing how you can go from this no field, very clean, strong resonance to this split feature here and suppression of the cross section. And so you get a transparency. So if you sit here and do an experiment where you look at transmission, you can get an enhanced transmission, sort of a transparency. And there's a 3-level model which can explain the basic physics. I'm sort of running out of time, so I'll go a little bit quickly. So here's an experiment. I won't dwell on this. It was not an easy experiment with the femtoslicing beamline. If you're interested in details, we have a paper. So here's the main measurement, which is showing the enhanced transmission through a gas cell when you have the laser imposed for the 2 polarizations. And so there's some details here, which I'm going to just gloss over. But you see the biggest effect with the parallel polarizations. And this is sort of, if you have the wrong polarizations, then you still get some you still have a strong laser field there which can field ionize the Rydberg states, so that's why you see a small effect here, basically. But okay, let's just move ahead here. So what I wanted to get to was to this. I'm near the end of the talk. Is that what I'd really like to do is to go beyond that absorption measurement and start looking at the Auger electron. So there's sort of a diagram of the experiment one might do. Here's that 3p and 3s core excited states. So if you have a weak X-ray, then you could be up here and have a strong optical field here to couple these, and then in principle look at the Auger decay from those states as you switch population around and see that signature in the resonant Auger spectrum here. The other thing is that because there's a strong laser field here, you can also field ionize these states. And so one question I'd like to ask is, could you recapture those low energy electrons? So to me this is something interesting because it has to do with exploring this interplay between what I know about inner shell physics from one photon interactions to these more interesting combinations of optical lasers. One could also then have the strong X-ray field, see how that would modify things. So I think this is kind of a system that I would be interested in looking at. Just want to point out that there's theoretical work now going on with Christian and Antonio as a postdoc there, but also there's this recent paper from Professor Sederbaum's group. So work is going on theoretically. So I'm at the end here. So I just want to point out now, so I'm from this AMO physics group at Argonne, and these are the experimenters that we now have. We have 3 people doing theory for us, and a lot of really great collaborators. Very, very important to have these collaborations. So here's my take-home lessons. So something you could look for at storage rings in the future would be better femtoslicing. That's going on next. Twolevel is building new femtoslicing. Bessie is upgrading their femtoslicing. Berkeley's upgrading theirs. And also at the APS, we have this plan to do full rep rate, megahertz rep rate, picosecond X-rays, but that's a few years away. We're using this cryogenic RF cavities. But we already have the high rep rate lasers, so now you can do pump probe experiments very efficiently. That's a whole different talk on that. And then the other take-home lessons, these SAW CFLs, they're great for these sequential multiphoton processes and for pump probe. And we could see first hints of Rabi oscillations, but you really want these advances in the FEL development to increase the temporal coherence and other properties you'd really like, polarization control, reduce the bandwidths. So then you can start doing these more sophisticated experiments with quantum state population control. And then finally, one thing I'm interested in would be combining optical lasers with the X-rays to explore these core excited states. So thank you for your attention.